I love that. I love that slide. Or I love that quote. If you actually ever want a good quote, all you have to do is look at Yogi Berra and you'll find something. But that's really nice. I like that because the idea of perfection is abhorrent, really. Because the idea is once you're perfect, then you may as well just go kill yourself because there's absolutely nothing else to be done, you know? So perfection is the enemy of progress. And that's kind of like what I'd like to talk about a little bit today. But first, a little bit of history. I am teaching a course at SMU, and I notice I got a Mustang's shirt right in front of me here, on programming languages. And I'm kind of corrupting the youth by making them learn a new programming language every week. And not a single programming language has been less than twice their age old, as in, yeah. So I got them learning. My first language scared the crap out of them was Snowball. So anyway, so a bit of history. And I was going back and looking at history, and I reread Joe Armstrong's paper on a history of Erlang. If you haven't read it, it's really quite fun. And it's full of Joe-like quotes. So in 1985, when I joined the lab, I asked my boss, Bjorn Jekker, what I should do. He just said, solve Ericsson's software problem. Here's Joe Armstrong. This seemed to me at the time quite reasonable. But you know, after a while, I realized it was a bit more difficult. So their problem was they had these new, or relatively new, solid-state exchanges that they needed to write software for, and that software needed to be reliable. And they had already come to the conclusion that they wanted to move away from procedural programming and start looking at declarative programming. So Joe spent some time looking at languages, and first code, they actually had like a little test exchange plugged into some deck, something or other. He first coded that up using Smalltalk and decided he didn't like that. So his next attempt was using Prologue. And so this is actually a Prologue program that he wrote that pretty much did the entire part of the test. I mean, obviously there's some support stuff in there, but this was the main program of the test. And it compared to hundreds and hundreds of lines of code on, you know, the other examples. And it was declarative, which is what he liked. So he kind of liked this, but Prologue at the time was a single-threaded application. So you wrote your code and it started at the top and went down to the bottom and, you know, eventually terminated. So being Joe, he said, okay, it's a pretty simple language to implement, so I'm going to implement a parallel version of Prologue. And he did. So he came up with a parallel version of Prologue, which didn't quite do what they needed to do, and he basically mutated it into Erlang. But let's go back and pretend he didn't. Let's go back and pretend he actually stuck with Prologue for a little while. How many people here have programmed in Prologue? Oh my word. Over there, is this kind of like, is this like, did you put sections up? This is the declarative section over here. So that's cool, all right. Yeah, right, yeah. So I'll wait till you guys backtrack and then I'll go this way. All right, so Prologue. For those of you who have not programmed in Prologue, Prologue is designed for programming based on predicate logic. And in Prologue, it's a very simple syntax. We can specify facts. So here are 6 facts about trees. In this case, we have a predicate, either evergreen or deciduous, and then we have an atom, which would be :u if it was an elixir, right? And what this is saying is ash is deciduous. Or you could actually put it slightly more kind of like the way Prologue sees it, deciduous ash, that's hard, deciduous ash is true. Okay, so that's how you express facts. Is it me or does this keep cutting out?
We'll switch it out.
And then Bruce said, all right, okay, queries. So you can actually the main way you interact with Prologue is by making queries. And a query is actually a way of saying to Prologue, this is not true. And then Prologue, being a computer, says, you're a fool. Of course it's true because of this, this, and this. Right? So I can say, I don't think evergreens are a pine. Sorry, pines are an evergreen. And Prologue will say, idiot, because I found one already. Right? It's true. Right? Is ash an evergreen? No, it's not. Is oak deciduous? Yes. Okay, and that's simply by looking at these facts. Obviously, it doesn't know about deciduous and ash and everything else. Where it gets cool, though, is that this is basically saying, hey, go search for facts, right? We could do this with a regular expression or pattern matching. But we can also say, is X deciduous? X, uppercase, means variable. So what I'm saying is, I am defying you to find a way of making this true. And Prologue says, you fool, I can make this true if X is ash. But wait, there's more, it says, because I can also make it true if X is cherry and if X is oak. So Prologue is doing more than just simple pattern matching. It's actually doing a fair amount of work to actually look at all the various possibilities, which I think is kind of cool. So we've had a look at facts, basic queries. Now we can look at predicates. And a predicate is where I can get the if part in. So here, what I'm saying is, X is a tree if X is deciduous. Yeah? I can also say X is a tree if X is evergreen. So I can say, is pine a tree? And in this case, it's going to go, well, pine is not a tree, but I know that if X is evergreen, then it's a tree. So can I find an evergreen that's called a pine? Oh, yes, I can. Therefore, yes, that's true. And again, I can say, is X a tree? And it's going to go one level deep as it searches for my trees and come back with everything, which is kind of fun. But wait, there's more. So here I have the density of the woods of the trees. So pine, I think, pine is the lightest. And what's the heaviest? Ash, I guess, is the heaviest, per cubic, whatever. And here I've written a predicate that says X is denser than Y if the density of X is dx and the density of Y is dy and dx is greater than dy. Okay? So now we're getting a fair number of levels deep into, working out what's trying to go on here, right? It's doing a lot of searching around here. But that works fine. So is cherry denser than oak? No. Is cherry denser than pine? Well, yeah, everything's denser than pine, right? But then we can do cool things like, what is cherry denser than? Right? I define something that cherry is denser than, and it says, oh, I know, pine. And you go, okay. Or you can do the other way around, right? What is denser than you? And in my case, nothing's denser than me, but I thought I'd say it before someone else did. Okay. So just one more kind of proper example. I'm trying to answer the question, which deciduous trees are denser than every evergreen? Yeah? So which deciduous trees, you cannot find an evergreen tree anywhere more dense than this deciduous tree. So I'm saying that D has to be deciduous, E has to be an evergreen, and D has to be denser than E. And if I feed that into my Prologue program, it comes back and tells me ash is the only one that matches that. Notice that I am not telling it how to do anything. All I'm telling it is information of what I know or what I want to know, and let it work out how that actually is going to work. couple more examples. All right, let's do some math. So this doesn't, okay, the octothorpe, the hash character there, just means that I want this to be a constraint and not an equality thing. So I'm saying that, can you find an A such that A equals 3 plus 4? And smartass Prologue says 7. All right, can you find an A such that 7 equals A plus 4? It says, sure, 3. Not a problem. Now I've got two variables, B equals A plus 4, so the best it can do is tell me that there's a constraint here. A plus 4 is going to be the same as B. Then I could say B plus 3 equals A plus 4, and it says, well, in that case, B is 1 more than A. And just to put this in perspective, Prologue came about in 1972, I think. Let's take it a bit further. And I discovered this because my SMU class said to me, I bet you can't do this, right? So let's solve the quadratic, x squared minus ax plus 15 equals 0. And to do that, all I'm going to do is write that equation down. X times x minus ax plus 15 equals 0. And I had to kind of give it a hint about some kind of range for those numbers. And smartass Prologue says, well, here we go. Actually, the constraint that comes out of this directly is that x is going to be 3, 2, 5. So I said, that's not good enough. Right? I want to know exactly what it is. So I'm going to force you not to give me a constraint, but to give me actual values. And I do that by sticking label on the end there, and it comes back and says, oh, all right, x equals 3 and x equals 5. Not bad for an old creaky piece of software. Bit more. You know this kind of puzzle you see sometimes, right? So this it's called a cryptarithmogram or something like that. And the idea is you're supposed to make this true because you assign a different digit to each letter, but an E there has to have the same digit as the E there, has to have the same digit as the E there. So each letter gets a different digit. The digits are unique across the letters, and you can't start with a 0. Now, otherwise, I mean, yeah, whatever. So how would you go about expressing that in Prologue? Well, here's what I'm defying it to find. Send plus more equals money. Pretty straightforward. Now I have to do a little bit of housekeeping because I have to work out what the unique digits are in this. And I could get Prologue to do it for me, but I don't know how. So here's my unique digits. Oops! So those are my unique digits. And yeah, I also know that each of those has to be a number between 0 and 9. I mean, otherwise it could be a tree, yeah? So I'm constraining my digits here. So ins with the plural means it applies to every element in that list. I also know that the beginning S and M have to be greater than 0, because that's what the problem says. And I also know that all the digits have to be different. And then finally, I know that if I do that addition, it should be true. And although it's formatted to look like that addition over there, it's just literally an equation, right? 1,000 times S plus 100 times E plus blah, 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 equals that. And then finally, I say, and I don't want you to start being all clever with me, I want you to give me the actual answer. So I say, label the digits. And I do that, and pretty much instantaneously, Smalltalk comes back with that, which means that that's the solution to my crypto whatever-ogram. Almost feels like cheating, doesn't it? So what have we done here? What we've done is taken a problem that was expressed in terms of constraints. And we've basically implemented the solution by telling a computer what those constraints were. Now, you probably do this most days if you use databases, because it's the same kind of way that SQL works, right? You don't tell SQL, go to this table, read the next 4 bytes and do this, right? You say, you know, is there a person whose department is this and whose salary is less than that? And it goes and works out how to get that. So this is constraint-based programming, and it has a lot going for it. If you can work out the constraints, then your programs are typically way, way shorter and way less buggy. The problem is, you can't always work out what the constraints are. At which point I would say to you, what the hell are you doing programming if you don't know what the constraints are? If you don't know what the constraints of the thing you're producing are, then you shouldn't be programming it in the first place because you don't know the constraints, right? So ultimately, yes, it's harder at some times, but it shouldn't be. All right, so that's Prologue. We'll come back to it. Now let's go back to Joe. All right? Young Joe. So as I said, he tried Smalltalk, and then he tried Prologue, and he came up with Prologue, and then said, no, I'm going to switch to Erlang. And part of the reason of doing this is just to show you something kind of interesting. Because a lot of people go, wow, Erlang's got some funky syntax. Yeah, really strange. Well, side by side, Erlang syntax is basically Prologue syntax. Variables are uppercase. You have commas between clauses. You have full stops or periods at the end of sentences. You have pattern matching. And last, but by no means least, you've probably read that the Erlang process scheduler will reschedule processes either when they block or after they have done so many reductions. And then someone will say to you, oh, and reductions, that means kind of like function calls, kind of, right? Now, go back to when Joe implemented his concurrent Prologue. In Prologue, it searches a problem space looking for answers. And to do that, it has a stack on which it keeps things that it's thinking about. And every now and then, it can merge 2 things on the top of the stack to say, oh, this and this, if this and this are true, then this predicate tells me that this is true. So it can take the top 2 things off the stack, or 3 things, or whatever, and replace them with 1. And in Prologue, that's called a reduction. And every time his Prologue interpreter made a reduction, he switched across to work on a different thread or a different process. So that's why Erlang calls them reductions. So now you can show off when you go to Erlang parties. Because if you go to Erlang problems, you definitely need something, you know. Okay. Part 2. And for people who are getting worried, it's part 2 of 2. I think we have a problem. And to illustrate that problem, I have created a nice simple infographic. We have the rest of the world, we have the Erlang community. That, to me, is the tragedy of the beam. Wow, that'd be a good band name, wouldn't it? Yeah, oh, I play for the tragedy of the beam. Anyway, the tragedy of the beam is we have some very successful technologies. And everybody likes being affiliated with success. And so that's what we run with. You know, it's kind of like, I mean, I don't know a thing about sports, so I'm making this up, but it's like a football team that has a really, really effective offense, that, you know, one particular pattern it runs, and so it runs it all the time because that's what works, you know? And don't get me wrong, they are very nice technologies. They're very, very cool technologies. They're very well implemented technologies. But they are not the only technologies. If anybody is stupid enough to post anything on any of the Elixir groups to say, maybe this shouldn't be done with Phoenix. Oh, right? If you post something about, oh, I don't think we should be using OTP for this, you would not believe the vitriol that comes down. OTP has been in development for 30 years. OTP is the only way of handling all of these processes. OTP is fantastic because we don't understand it. That last part is true. So, let's turn to Rear Admiral Grace Murray Hopper. The most damaging phrase in the language is, we've always done it this way. Everybody shows pictures of Grace Hopper when she's like 107 years old. That's actually, I think, I mean, as far as I can tell, that's actually a picture of her back in the late 50s. And if you want to see just how smart this lady is, look at the eyes in that picture. They are scary. Smart. All right. So, Bruce, next time you do a conference for the Elixir community or the Beam community, I would like you to use, you know, rather than misspelling Elixir, I would like you to have... The new motto, which I've invented for the community, doing old things better. Trademark, so you have to give me like a 10% on each one. But that's kind of, I mean, I kind of like being a wee bit kind of like, whatever, controversial or something. But I genuinely feel that this is a tragedy. Because that's how we see ourselves. You know? Rails. We can do better than Rails, right? We've got Phoenix. Or, you know, running 1 million processes on your computer? Of course, we got OTP, you know? And that's what we do, is we look at old existing problems and say, wow, with this technology, we can do them so much better. I don't want to do that. I want to do new things. And here's the thing. Whenever you do something new, you guarantee that you're going to do them badly. Right? You've never done it before. You're going to mess up. And people use that as the reason not to change. Yeah, I could probably do it better if I didn't use OTP, but if I make a mistake, it won't work. And it'll be my fault. But if I use OTP, it'll be their fault. Right? So we're going to do things poorly. That is exactly what we're supposed to do. And one thing we don't embrace as a community is failure. We have this thing that we're better than everybody else. And what we do is great. We have the best technologies, we have the best virtual machine, blah, blah, blah. And we are not prepared to be anything other than world class. And let's not make a mistake, we are world class. But we're kind of defining ourselves by that. So all we can do now, we cannot attack anything unless we can be world class. And when we're going to do something brand new, we're not. We're going to be doing it badly. And then if we're lucky, we could be doing it adequately. But who knows? Eventually, we might be doing it really, really, really well. So we have world class. You can read the list. I don't have to read the list to you. Yes, I do, because you're in the corners there. Runtime, libraries, tooling, experience, and people. I mean, literally, world class. Let my people go. Let them loose. Let people experiment. Don't put them down with, ooh, we've never done it that way before, right? Let them loose. Let them create a future. There you go. So that's a small problem, okay? Because the problem is, well, okay, what actually is the future? So I went and I asked academics. Didn't get any consistent answer. I went and asked consultants, and they tried to charge me. I went and asked developers, but they never think about anything more than the next 5 minutes. I kind of ran out of ideas until I suddenly thought, oh, I know someone that knows the future. So I went to Zoltar, and just like the consultants, he wanted to charge me, but it was only 50 cents. So I put my 50 cents in, and I got the card. Now you know that the card here is always something totally anodyne, right? It's always something like, you will have an exciting day that will make you think of the future, right? Well, for some reason, this time Zoltar was really on. I predict that in the future, software will be written as small decoupled components that interact over a dynamic and involving large-scale network. Your favorite color is purple. And I don't disagree with Zoltar, which is kind of surprising. I honestly think that if I look to a future, and I don't mean here next year, but 5, 10 years from now, I see an environment, right now there's what, 150 people in this room. If you combine our phones and the laptops you've got sitting on the floor, we've probably got a teraflop or more of processing capability, doing absolutely nothing right now, which is crazy. Why can't we have a swarm of little intelligent components wandering around solving problems for the world using all of these resources we've got? And the more I think about that, the more I want to see it happen. I want to see this kind of, well, I'm kind of calling it component soup. That slide took me about 3 hours, so. But here's my point. We could be the people that make this happen. We have so many of the right things in place. And by we here, I mean the Beam community, right? Everybody involved. Well, how are we going to do that? Well, let's go back to the roots. Let's go back to Prologue. It's a declarative language, it's immutable, it's pattern matched, and it's mathematically sound. All of the things in here are exactly what we need in a large-scale distributed environment. Declarative, because it solves its own problems. Immutable, because we're not going to get corruption of state. Pattern matched, so we don't have to specify everything up front. And mathematically sound, so that we can actually reason about things. For what it's worth, that kind of sounds a bit like a definition of bitchain. Blockchain, sorry, blockchain. Bitcoin, blockchain, you know what I mean, right? Related to Prologue again, back in the, I think, late 70s, someone produced something called Datalog. It's not a product, it's simply a terminology. Datalog is a subset of Prologue that you can use to reason about databases. So most databases, big databases, when they come to add a feature or whatever else, they mock it out in Datalog first to see how it's going to behave, because they can prove Datalog code. A lot of the ideas in Datalog, like recursive subqueries, make it back into SQL. And there are a surprisingly large number of implementations of Datalog, some of them wrapped into existing databases, and some are actually essential to the database. So Datomic, for example, uses Datalog as its query language. If you've not come across Datomic, shame on you. It's a transactional write-once database. It's, well, this comes off the website, but it's row-oriented, column-oriented, graph-oriented, hierarchical. You can time travel using it, and it uses Datalog as a query language. And if you want to know more, Stu's in the corner there, and I'm sure there's conference discounts. So what? All right, another technology. This is all building to something, I promise you. Tuple Spaces. Tuple Spaces are a technology, and I have no idea why this didn't take off. The idea of a tuple space is that we basically create a cloud full of facts expressed as tuples. And we can search those facts by using pattern matching. And we can then update those facts, well, not update, add new facts based on that. When we search, we can say, if I find something that matches, remove it from the blackboard. And when I add something, I can say this will only live for the next 100 seconds, or whatever it might be. Talking about Pragmatic Programmer, this is actually a diagram in Pragmatic Programmer. Also took 3 hours. But if you watch these programs on TV, right, every single TV program right now is a police procedural or cooking show, right? So they all have some kind of blackboard. And on the blackboard, they all write the facts and the names and the dates. And one of the reasons they do that is that blackboards allow a whole group of people to cooperate on something when they're not physically together. You know, they can come in, they'll notice there have been changes, and they'll go, oh, wait a minute, that triggers a memory, and I've got to draw an arrow around that, or draw a line around that, and an arrow over here, and whatever else. Right? In the dramatic parts of all these police procedurals, you always have the lone, slightly rogue detective sitting on the edge of the desk looking at the blackboard. And then after 30 seconds or just before the next commercial break, he'll go, or she'll go, aha, right? They work. And we can organize our applications around blackboards. So what again? About 6 years ago, a guy called Neil Conway came up with this idea called Daedalus. Daedalus is Datalog, which includes a temporal dimension to it. And what this means is that you can have data with multiple people writing to it at the same time, and it maintains integrity without locks, without CRDTs, it just works. And you can query it based on that. So because each piece of data, each fact, has a monotonic timestamp, you can query and say, yeah, that's true, but what was it like in December? And it can tell you. So what? Imagine. So that's the gorilla picture I found when I went to Unsplash and said, imagine. But then as I was looking at gorillas, you know what it's like, right? So, you know, day and a half later, I came across this, which I think must be my favorite ever animal picture. All right. So what have we got? We have a kick-ass virtual machine that allows us to run a zillion processes that don't interfere with each other, that networks seamlessly, relatively seamlessly, low overhead, runs on devices ranging from Pis up to supercomputers. We have ideas of using pattern matching in a declarative way with predicates to both discover information and also create new information. By using information from Daedalus, we can then also manage that in a consistent way without any concurrency issues. So we have all of these various technologies that we can start combining together and using. So imagine that in future, what you're doing is you are just creating components and data and just throwing them into the soup. And when I say component, I mean 5 lines of code. I mean a fact. And you just literally throw it in there. Each component is effectively a reducer that gets invoked by a pattern match and which interacts with other components using pattern matches. All data is read-only, and all data is unique. If the string Dave Thomas is in there as data, it's only in there once around the entire world, because it doesn't need to be duplicated. And, as I said with Daedalus, all our data and our components are time-stamped, which means that suddenly software updating becomes non-issue. Yeah? Because a component can deal with data, and both are time-stamped, unlike the current situation with OTP, where a component actually has to manually map its data as it changes versions. And because timestamps can be part of the pattern match, history is available orthogonally throughout the entire system. Imagine having a network that has no topology, because you don't need one. It's soup. Yeah, sure, there's an implementation, but you don't care about that any more than you currently care how does a packet get routed from here to Dallas. You have no idea. And you don't care. Network with no topology takes it a step further. How about we have data with no location? Again, we don't need to care. It can just be out there. And yeah, that's a whole bunch of potential problems. Security is not the smallest of them, right? Performance is going to be an issue. But the concept is, I think, an incredibly powerful one. Information with full history. If all your information is guaranteed to be read-only, then people cannot change things and claim them always to have been true. Systems with no center. The idea of writing an application is so 1970s, right? We don't want to be doing that, because if nothing else, it assumes we know what's required, and we don't. Instead, what we're going to be doing is writing lots of small little components and making sure that they can interact in such a way that they can be combined by our end users to produce the result that they want. Think of it being more like a spreadsheet, where you contribute by adding new functionality and new UI elements and stuff, but you don't tell them, now do this, now do that. Our apps instead are going to be assembled on the fly by their users. That really does sound kind of scary. And it sounds like it'll never work. It's out of control. right? It's going to be hacked like crazy, blah, 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 right? There's always people that say, oh, that's not going to work. Is it based on OTP, right? Well, you know what? That is going to happen. We have no choice. It's already happening. Think about how applications are being written today. We're sticking their Lambda functions up in the cloud, and we've got remote databases and all sorts of horrible, scary glue that connects it all together. Right? It's happening. It's happening slowly, but it will happen. And yes, it will be absolutely horrendous. It might actually cause the end of the world. Seriously. No, I am serious about that. The whole world comes to rely on connectivity, applications, credit stored in banks, all of this kind of stuff. And we sit there and produce a system that one day just melts. The world would stop. People will die. So if we allow this to happen the way that we've been allowing things to happen so far, it will be a nightmare. I am not joking when I say it could be the end of civilization. Unless we do it on purpose, unless we plan for it, unless we think about it, unless we prototype it, unless we ship the idea out and allow 1 million people to criticize it, and then we refine it, and we let them criticize it again, and we keep refining it, we keep prototyping it, we keep trying it, and we gradually make it better and better and better. That's what I want to see us doing. Not rewriting Rails applications in Phoenix. So I'm sorry, I know you just printed the t-shirts. Let's get rid of doing old things better as our motto. Doing things that no one else has done. Yeah, sure, you can still get paid for writing Rails apps. But let's play with new stuff. Let's play with exciting stuff. Let's not just fix technology. Let's change the world. And while we're doing it, let's have some fun. Thank you.